Hi friends, this is Mira and welcome to Learn Engineering. In today's video, we will discuss dynamics. I wasn't very much fond of dynamics when I was a student myself, and I think many of you are in the same boat too. So, I worked harder to make this video more understandable, and I really hope that you like it. So, basically, in this video, we will discuss the basics of dynamics and also rectilinear motion in detail. So, let's get started. Dynamics deals with accelerated motion of the body, where velocity of the body is changing over time. Thus, in any engineering problem, wherever the structure or body is moving, principles of dynamics are used to find solutions. For example, the structural design of an airplane or any automobile need dynamic study. I know this is impossible. Also, design of mechanical devices like motors or pumps, and even prediction of movement of artificial satellites or spacecraft are based on the principles of dynamics. Analysis of earthquake forces acting on a building or vibrations on a bridge due to movement of vehicles also need dynamic study. In general, dynamics is divided into two parts, kinematics and kinetics. Kinematics is the branch which studies the aspects related to the motion of the body. That is, what is the velocity of the moving body, what is the acceleration, or what is the position or displacement of the body. It does not take account of forces involved in the motion. Kinetics, on the other hand, is the analysis of the forces causing the motion. In this video, kinematics of particles will be considered. Here, particles word does not mean literally very small particles. They can be as large as a rocket or an airplane. But it indicates that even if body is rotating about its own mass center, if the size of body and rotation is negligible as compared to the total displacement, then motion of bodies as an entire unit will be studied. If in some cases the rotation is not negligible, the bodies cannot be considered as particles but rather considered as rigid bodies. Dynamics of rigid bodies will be covered in the upcoming videos. A particle moving along a straight line is said to be in rectilinear motion. Movement can be in horizontal or vertical direction, but it should be in straight line. Now, we discussed that kinematics of a particle can be studied by specifying particle's position, velocity, and acceleration. Let us understand these terms first. At any instant of time, particle will be at certain position on the straight line. Let's say this pickup truck is standing at position P and a light pole is considered as a reference point which is at position O. The distance of vehicle from pole is x meter. If the truck moves from point P to another point whose distance from origin is x dash meter, then displacement delta x is x dash minus x. The displacement is positive if it is on the right side of the origin and negative if on the left side. But sometimes the displacement of particle may be different from distance travelled. Let's say the same truck is standing near the pole at position O. To reach the destination at P, it travels up to distance of x meter, then take a U-turn and travels back for distance x plus y meter. Then distance travelled xt will be the total distance between origin O and P that is 2x plus y meter. But the displacement will be the change in position, that is minus y meter, as it is on the left side of origin. If the particle moves through a displacement delta x during time interval delta t, average velocity of particle is delta x by delta t. To find out instantaneous velocity, that is velocity at any particular instant, we have to take a very small value of delta t, which will result into very small value of delta x. So instantaneous velocity v is equals to dx by dt. Here velocity is related to displacement, that is final change in position only. But if we talk about speed, it is related to total distance travelled xt. So average speed of truck will be total distance travelled xt divided by time delta t. Suppose at position P, the velocity of pickup truck is v, which is changing to v dash at p dash. Then average acceleration of truck is delta v by delta t, where delta v is difference in velocity. Similarly, instantaneous acceleration will be dv by dt. If we put v is equals to dx by dt, we get a is equals to d square x by dt square. If velocity increases, acceleration is positive. Negative acceleration is called deceleration. Another expression can be obtained by comparing these two equations. So we get a dx is equals to v dv. We discussed that if position of particle at every instant is known, motion of particle can be easily calculated. But in practical situations, it is not necessary that motion is defined by relation between x and t only. There might be relation between any two of the position, velocity, acceleration or time. For example, a free falling body will have a constant acceleration of 9.81 meter per second square. So we will get a graph of acceleration versus time. But if an object attached to spring is stretched, velocity of spring will depend on how much stretching is applied. Here, different value of velocity for different elongation can be measured. So, velocity versus position graph can be plotted. Now, if graph between any two variables is given, then how to develop subsequent graphs between other two variables? Let's see. If a simple position to time xt curve is plotted for pickup truck which is moving in positive direction, then stops and takes a U-turn and again moves in opposite direction. Velocity time curve, which is called Vt curve, can be constructed using equation v is equals to dx by dt as it involves x, v and t. Here dx by dt is nothing but slope of xt graph. So by taking slope at different points 1, 2, 3 and 4 on xt graph and measuring dx and dt, we can plot Vt graph. This is graphical method. But if some mathematical expression is given between x and t, velocity can be calculated by differentiating this equation so that v is equals to dx by dt. Similarly, if Vt curve is given, At curve can be plotted using equation A is equals to dv by dt. So again, slope of Vt curve at different time gives At curve. Analytically, acceleration can be measured by differentiating equation of V. Here you can observe that differentiation reduces the polynomial by 1 degree. Then suppose the xt graph is a second degree curve, that is a parabola, then vt graph will be a first degree curve, that is a straight line, and the at graph will be a horizontal line, that is 0 degree curve. But if the graph is given in reverse order, that is if at graph is given and vt graph is to find out, then we have to use equation A is equals to dv by dt. As we need to find out v, by integrating both sides, we get change in velocity delta v is equals to integration A dt. So if we take any point 1 at time t1, area under at graph gives change in velocity. If we plot this delta v1 for initial velocity v0, we get v1. Likewise, mark v2 for time t2 and so on, and we get vt curve. Similarly, v is equals to dx by dt, so change in position delta x is equals to integration v dt, and so area under vt graph gives change in position, and by same method we can develop xt curve. If the particle is moving with constant velocity, it is called uniform motion. So v is constant and acceleration, that is change in velocity, is 0. To find out position coordinate x, integrate this equation for initial position x0 at time t is equals to 0 and final position x for time t. We get x is equals to x0 plus vt. But remember that this equation can be used only if the velocity of particle is constant. In case of uniformly accelerated motion, particle is moving with constant acceleration. In this case, velocity of particle is changing constantly with time. As we discussed, a free-falling body is an example of uniformly accelerated motion where acceleration is constant, that is 9.81 meter per second square. This is a useful concept in solving numerical. Here, velocity is obtained by integrating this equation for initial velocity v0 and final velocity v. So, v is equals to v0 plus at. To find out position coordinate x, put v is equals to dx by dt and integrate this equation for x0 and x. We get x is equals to x0 plus v0t plus 1/2 at square. We derived one more equation in the first part of this video, v dv is equals to a dx. By integrating both sides, we get this equation. These three are very useful equations to solve problems analytically, but again they can only be used if the acceleration of the particle is constant. When several particles are moving along the same line, their movement can either be independent or dependent to each other. If several balls are released on a slope at same time, they move along a straight line in same direction, but they are independent to each other. In this case, relative motion of particles is measured. Suppose two independent particles A and B are moving along same straight line and their position from origin O at any instant t is xa and xb respectively. Then the relative position coordinate of B with respect to A is equals to xb minus xa. So we get relative position of B, xb is equals to xa plus xba. Similarly, rate of change of relative position gives relative velocity. So Vv is equals to Va plus Vba. and rate of change of velocity gives relative acceleration of B with respect to A, and so we get this equation. These equations are valid for independent motions only. But in a system of pulleys and cables, position of block B is dependent on position A. If block A is moving, block B will also move. Thus, if the position of a particle depends upon other particles, then this is called dependent motion. The relation between position coordinates in this case can be written in the form of an equation. Let's see how we can derive it. Let's say A and B are at distance XA and XB respectively from the ceiling. Here we are interested in the changing or variable part of the rope because that will affect the positions of A and B. We won't worry about the part of rope which is constant. So here total length of rope from A to G is constant. Also portion CD and EF of rope are wrapped around pulleys, and as the diameter of pulleys are not changing, these lengths are constant too. Only length of segments AC, DE and FG can be changed. But as the total length of rope is constant, summation of length of these three segments is also constant. Now how can we find lengths of these individual segments? So we have measurement XA for block A, but that is measured from ceiling. Now the first pulley is fixed. So this distance is going to be constant, anything like 0.5 meter or 1 meter or 1.5 meter. We are not interested in value of constants right now. So AC can be written as total distance XA minus constant. Similarly, DE and FG is XB minus constant. So we get equation XA plus 2XB is equals to constant. If we differentiate this equation, we get a relation between velocity of particles. Again, by differentiating velocity equation, we get relation between acceleration. Now, if block A is moving in downward direction with acceleration of 1 meter per second square, block B will move in upward direction with 0.5 meter per second square acceleration. Thus, if block A changes its position or moving with some velocity or acceleration, block B will have half of that amount but in opposite direction. Likewise, we can derive equations for any system of particles.